When NASA's New Horizons spacecraft streaked past Pluto in July 2015, it delivered something humanity had never possessed: an intimate portrait of a world that had spent nearly a century as little more than a smudge at the edge of our telescopes. This frozen wanderer, dismissed for generations as a dead, featureless ice ball, revealed itself to be a world of staggering complexity. Nitrogen glaciers sprawled across basins the size of Texas. Mountains of water ice, hard as granite in the extreme cold, jutted skyward. And wrapping the entire globe like a delicate veil, a thin, ghostly atmosphere shimmered with dozens of layered hazes, scattering sunlight into an ethereal blue glow. It was breathtaking. It was revolutionary. And it was wrong. Hidden within that beautiful data was a number that made no sense. When scientists measured Pluto's atmospheric temperature, they found approximately 170 Kelvin. But every climate model predicted 100 Kelvin. Pluto was inexplicably 30 degrees colder than physics said it should be. Something was actively refrigerating an entire world. But what? For years, this cold case haunted scientists. Then, in 2017, a radical hypothesis emerged. And in 2021, the James Webb Space Telescope finally had the power to test it, confirming what was once called a crazy idea and revealing Pluto to be far stranger than anyone imagined. For most of the 20th century, Pluto remained one of the great mysteries of our solar system. More than 5 billion kilometers from the Sun, it appeared through telescopes as nothing more than a faint, flickering dot. Astronomers knew it was small and icy, about 2/3 the size of our moon, and suspected it might have a thin atmosphere. But beyond vague ideas, no one really knew what Pluto was like. That's why NASA's New Horizons mission was critical. Time was running out. Scientists feared that if the spacecraft wasn't launched by 2006, it wouldn't reach Pluto before its atmosphere potentially froze and collapsed onto the surface. If that happened, humanity could lose its only chance to study Pluto's atmosphere up close, possibly for centuries. New Horizons launched right on schedule in January 2006. After a 9-year journey across the solar system, it finally reached Pluto in July 2015. What it discovered stunned the world. The dwarf planet's heart-shaped region, later named Tombaugh Regio after Pluto's discoverer, gleamed with nitrogen ice. Vast glaciers flowed across ancient basins. Mountains built from water ice rose kilometers into the black sky. And above it all, a fragile, layered atmosphere extended more than 300 kilometers above the surface, glowing with an otherworldly blue haze. Pluto wasn't dead. It was alive with geological activity. But as scientists analyzed the data, a troubling discrepancy emerged. Pluto's atmosphere, composed mostly of nitrogen with traces of methane and carbon monoxide, should have behaved predictably. Existing climate models, the same ones that accurately described atmospheres on Earth, Mars, and Titan, predicted an atmospheric temperature around 100 Kelvin. The actual measurement? Approximately 70 Kelvin. This wasn't a minor error. A 30-degree difference represented a fundamental failure of our understanding. The models accounted for solar heating, atmospheric composition, and radiative processes. They had worked everywhere else. Why were they failing at Pluto? Scientists checked and rechecked the data. The instruments were functioning correctly. The measurements were solid. Reality simply refused to match the equations. Something unknown was cooling Pluto's atmosphere far more efficiently than any known process. The hunt for an explanation began. To understand what might be happening, researchers turned their attention to Pluto's most visually striking feature: its layered blue haze. This haze forms through a remarkable process that begins with an unlikely ingredient: sunlight. Even though Pluto is incredibly far from the Sun, ultraviolet rays still reach it. These rays carry enough energy to break apart methane molecules high in the atmosphere. When a methane molecule gets struck by UV light, it splits into fragments, a methyl radical and a hydrogen atom. These broken pieces don't simply float away. They begin reacting and combining, forming more complex hydrocarbons like ethane, ethylene, and acetylene. But the process doesn't stop there. These molecules continue combining and growing into even larger, more complex compounds. Eventually, they form solid, tar-like particles called tholins, tiny bits of organic matter that give Pluto its distinctive reddish-brown coloring in certain regions. As these tholin particles slowly drift downward through the thin atmosphere, they gather into distinct layers. These layers scatter sunlight, creating the soft blue glow that New Horizons captured so beautifully. The haze was stunning. But could it also be the key to the temperature mystery? In 2017, planetary scientist Dr. Shi Zheng proposed a radical idea. Traditional climate models focused on gases. Gases absorb solar energy and radiate heat in specific ways, and these processes determine atmospheric temperature. But Zhang suggested that on Pluto, the solid haze particles might be more important than the gases. Here's the concept. Those tiny tholin particles floating in the atmosphere absorb incoming solar radiation. But instead of warming the surrounding gas through collisions, as happens in thicker atmospheres, they re-emit that energy directly into space as mid-infrared radiation. In essence, the haze was acting as a planet-scale cooling system. Every particle was a tiny radiator, intercepting heat and bleeding it into the void before it could warm the atmosphere. If true, this would overturn decades of assumptions about how atmospheres work. On Earth and most other worlds, gases dominate climate. But on Pluto, solid particles might be running the show. The hypothesis was elegant. It explained the temperature discrepancy perfectly. There was just one problem. Zhang's theory made a specific prediction. If the haze particles were truly responsible for cooling the atmosphere, they should be emitting radiation in the mid-infrared spectrum, wavelengths between about 15 and 25 micrometers. Detecting this radiation would be the smoking gun, but in 2017, no telescope could do it. Ground-based observatories faced an insurmountable obstacle. Earth's own atmosphere absorbs mid-infrared light. Those critical wavelengths never reach our telescopes. The Hubble Space Telescope, while above the atmosphere, wasn't designed for mid-infrared observation. Its instruments simply couldn't see in the right part of the spectrum. And there was another challenge. At Pluto's immense distance, the signal would be extraordinarily faint. Even if a telescope could observe in mid-infrared, it would need unprecedented sensitivity to detect the weak thermal glow of microscopic particles on a world billions of kilometers away. The theory sat in scientific limbo, a beautiful, untestable idea waiting for technology to catch up. In December 2021, everything changed. The James Webb Space Telescope launched from French Guiana aboard an Ariane 5 rocket. After a month-long journey to its orbital position beyond the Moon, Webb began unfolding its massive golden mirror and cooling its instruments to operating temperature. Unlike any observatory before it, Webb was specifically designed for infrared observation. Its 6.5-meter mirror could gather light with extraordinary sensitivity. And critically, its MIRI instrument, the mid-infrared instrument, could observe in exactly the wavelength range Zhang's theory predicted. For the first time in history, humanity possessed a telescope capable of testing the haze cooling hypothesis. Scientists began planning observations. Pluto would finally reveal its secrets. Observing Pluto with Webb presented unique challenges. At nearly 5 billion kilometers away, Pluto and its largest moon, Charon, appear almost as a single point of light, even to Webb's sharp vision. Their angular separation is tiny, less than 1 arc-second. Any observation risked blending their signals together, making it impossible to determine which thermal radiation came from Pluto and which from Charon. This mattered enormously. Charon has no significant atmosphere and no haze. If scientists couldn't separate the two bodies, they couldn't isolate the atmospheric signal they needed. Webb's team developed a careful observational strategy. By taking multiple exposures and using precise pointing data, they could mathematically separate Pluto's contribution from Charon's. The process was painstaking, requiring careful calibration and analysis. In May 2023, Webb turned toward the outer solar system and captured the critical data. The results exceeded expectations. When scientists analyzed Webb's mid-infrared observations, they found exactly what Zhang had predicted years earlier. Pluto was emitting excess thermal radiation in the specific wavelengths associated with solid particle emission, the unmistakable signature of haze particles radiating heat into space. The signal matched the theoretical predictions with remarkable precision. The haze wasn't just a beautiful visual feature. It was actively controlling Pluto's climate, absorbing solar energy and dumping it into space before it could warm the atmosphere. The decade-long mystery was solved. Pluto's atmosphere was cold because its haze was functioning as a planetary air conditioner, a cooling mechanism that had never been observed dominating a world's climate before. The crazy idea from 2017 was confirmed as scientific fact. The implications extend far beyond Pluto. If solid particles can dominate atmospheric cooling on one world, they might be doing so on others. Scientists immediately turned their attention to similar environments across the solar system. Titan, Saturn's largest moon, possesses a thick, hazy atmosphere rich in organic compounds. Traditional models have struggled to fully explain its thermal behavior. Could particle cooling play a role there too? Triton, Neptune's largest moon, shows evidence of atmospheric hazes and displays its own thermal mysteries. The same mechanism might be operating in that distant nitrogen atmosphere. Even early Earth enters the conversation. Billions of years ago, our planet's atmosphere may have contained significant organic hazes. Understanding how such particles affect climate could illuminate chapters of our own planetary history. The discovery forces a fundamental shift in how scientists model atmospheres. For decades, the assumption was simple. Gases control climate, and particles are secondary. Pluto proves that assumption wrong. On cold, hazy worlds, the particles might be running everything. Textbooks will need updating. Climate models will need revising. And every time astronomers discover a new hazy world, whether in our solar system or orbiting a distant star, they'll need to ask, are the particles in charge? Pluto waited at the edge of the solar system for nearly a century, guarding its secrets behind billions of kilometers of empty space. When New Horizons finally arrived, it revealed a world of unexpected beauty and an atmospheric puzzle that defied our understanding. For 8 years, that puzzle remained unsolved. The tools didn't exist to test the radical explanation. But science is patient, and technology eventually catches up to imagination. James Webb Space Telescope, with its golden mirror and infrared eyes, finally provided the answer. Pluto's blue hazes aren't just beautiful. They're functional, operating as a vast cooling system that dominates the dwarf planet's climate. In solving one mystery, Webb opened doors to countless others. Across the cosmos, On moons and planets and worlds yet undiscovered, similar processes may be shaping atmospheres in ways we're only beginning to understand. Pluto, once dismissed as too small and too distant to matter, has rewritten our understanding of how worlds work. The strange, frozen dwarf planet at the edge of everything turned out to be a teacher, showing us that even the smallest worlds can hold the biggest surprises. The universe, as always, is stranger than we imagined.